Hello everyone, I'm Mojtaba and welcome to another episode of A Sip of Chemistry. Glass science has numerous outstanding researchers worldwide. Steve Feller, a physics professor at Coe College, is among these remarkable people who have devoted their careers to exploring these fascinating materials. His expertise primarily lies in borate glasses, although he has also studied tellurite and silicates. In our conversation, he briefly explained his major findings in borate glasses in the past few years. He also gave his insight into challenges he faced during this journey. Interestingly, as a coin collector, he has also researched Camp Money of World War II. With his daughter, he has authored over 100 articles and wrote a book on this topic. I reached out to him for an interview and he graciously accepted. I'm pleased to invite you to watch this exciting interview with Professor Steve Feller. Thank you, Professor. Thank you so much for agreeing doing this interview. I'm glad that I have the opportunity to talk to you today. At the beginning, I would love to ask you about your academic background. Where did you get your degrees?
So my undergraduate degree was from Clarkson University in Potsdam, New York. The degree was in physics. From there, I went to Brown University, where I got my master's and PhD, and I did work there with a very well-known glass scientist, Professor Philip J. Bray, who was the first to do NMR in glasses in the history of the world. And I learned a lot from him. And from there, I went to Coe College in Cedar Rapids, Iowa, where I became a professor of physics 45 years ago.
So, how did you become interested in glass science?
Well, I didn't start off knowing much about it. When I went to graduate school in physics, toward the end of the first year, so this was the academic year 1973-74, we were instructed to visit groups and get to know advisors to make a connection at the end of the spring of 1974. And I went around and spoke to various professors, most of them not in glass. And then I came upon Phil Bray in glass. I met his students, and the fit seemed to be good. That was the moment I started studying glass, spring of 1974.
Your background is physics, right? You did your education in physics. So, how do you define a glass? What's a glass from your perspective?
From my perspective, a glass is a screwed up solid. It's a solid whose atoms do not form a regular pattern like a crystal does. So it is a solid. It's not a liquid. It's as rigid and as strong as many crystalline solids. Except that while it has short range order among the atoms, typically it does not go much past that, maybe 5 to 10 angstroms, at which point it becomes disordered. That's a solid to me. Now, since then, I've read and come to know that it has no long range order and it has a glass transition as well. So those two qualities, no long range periodic order, and the glass transition, that's a glass.
So, borate glasses are very highlighted in your research work. Why are you interested in borate glasses?
Well, the silicates have been much studied, certainly more than any other glass system. So that's one factor. when I went to Coe College, I decided that I would study using rapid cooling extensions of glass forming systems, and the borates have been very good that way. In that I've been able to extend their ranges of glass formation readily. Now, I do study other glasses besides borates. I've studied germanate and silicates. I have a paper coming out pretty soon on sodium silicates at very high alkali contents. But it's been the borates that have had the biggest impact. It wasn't planned that way. Part of that has to do with the fact that Phil Bray was the first to do boron NMR on glass. Mm-hmm. So from his group, I learned about boron in glass as well.
Okay. After plus 30 years working on borate glass, actually, uh, what you can tell us about these types of fascinating glasses?
They have a basic coordination change. So glass has been described as the universal solvent. You can add many compounds to basic glasses. There are only a few oxides, at least, that form glasses by themselves. Silica, germania, phosphorus pentoxide, and boron oxide come to mind. So when you add to boron oxide, say, in my case, I first added lithium oxide and went up to very high lithium contents. I can tell you that the structure is very much revealed in its physical properties in the borate cases and some of the other ones as well. But the borates were especially amenable to this because of the coordination change. So as the fraction of borons became more coordinated, typically the glass would become denser, the glass transition temperature would go up, the conductivity would change, the coordination change was mirrored in the physical properties in a very direct way. Mm-hmm. Now, when we first entered the business, if you would, of borates, in the lithium borate case, you could go up to about 30 or 35% lithium oxide pretty easily. And after that, the glass crystallized when cooled gently, shall we say. So what we did is we built roller quenchers, twin roller quenchers, which allowed us to go from about 30 or 35% continuously up to almost 75% lithium oxide. At 75%, there was an apparent wall, and the material crystallized at 75%. This was indicative of a structural unit, the last of the structural units that would make a network. Actually, it was the end of the network forming case when you had the orthoborate unit, a boron triangle with 3 non-bridging oxygens and no 4 coordinated borons. That material readily crystallizes, even with a roller quencher. You can't trick it, but you can go continuously from 0% modifier, 100% boron oxide, up to, say, 73% lithium oxide, 27% boron oxide, and make a glass. Yeah. So we did that, and we measured its properties for the first time. Up to that level, we measured the density and the glass transition temperature and such, and it was a beautiful system. It revealed the atomic structure. We went to sodium, and we learned a few different things about sodium. It had been reported in the sodium case that you could have 2 glass forming regions, one up to about 30 or 35%, and then a second one from about 70 to about 75 mole percent sodium oxide. Now, it turns out that that's using gentle cooling again. If you use the roller quencher and you start from sodium carbonate, you can get glasses up to about 48% sodium oxide, and then from about 52%. going on up to about 75%. And that's because at 50%, the meta composition, the material will crystallize. We now know that's because the metaborate unit forms a ring. In lithium borate, it forms a chain.
Mm-hmm.
The chain can be tricked and you can make a glass, but the ring cannot be tricked readily. It'll crystallize into sodium metaborate, N4 of 0, all borons with one non-bridging oxygen, forming six-membered rings. On the high end side, you can actually, with a roller quencher, go past 75%. You go to 80 or 85%, but careful measurements of the weights of the starting materials and the finished product indicate that you don't get a complete evolution of the carbon dioxide, and so you get carbonate retention in those materials. So what we did eventually was to start with sodium oxide itself in a glove box, and we learned that again you can go up to 48% and 52%, no glass at 50%, and then go up to about 73%, like in the lithium case, and then crystallization takes over without the presence of carbon dioxide. Now, that was a beautiful thing to see, that it was the effect of carbonate retention on the sodium borate glass that that allowed you to extend past the 75%. So there are complications that take place that are reflected in the ability to make glass. But when you start from pure sodium oxide and pure, now in the lithium case, you do get retention of carbonate, but only past 75%. So you get the natural glass forming range starting with lithium carbonate or lithium oxide. We did both eventually, and they're identical, the glass forming ranges. Potassium resembled sodium, rubidium resembled sodium, with that gap in the middle because of the ring structure, but cesium did not. In the case of cesium, you can go through the 50% range, and again, you get the carbonate retention at the higher alkali contents.
Mm-hmm.
So eventually, we mapped out the whole system. Then about 1988 or so, I began to see papers on these kinds of glasses come out of Greece, from Stratos Kamitsos' group. And so I had a sabbatical coming in the 1990-91 school year. And so I wrote to him asking him if he'd like a visitor. Now, this is kind of a funny story. He immediately said yes. And so I took my family on an amazing trip to Greece in the fall of 1990. Amazing. Because we took a boat and train from England to Greece. And when we got to Greece, there were national strikes, and it was chaotic. But I tell you this, working with him was worth it. He was a very, very fine scientist and person. And when I wrote to him, I really didn't know him. But it turns out he knew me, both from the papers. I mean, I knew him through his papers. He knew me through my papers. But it turned out he had gone to Brown also. I didn't know it. He was in the chemistry department at Brown. He had gone from Greece to Brown, and he knew of my advisor because Stratos was studying glass with a guy by the name of Bill Risen in the chemistry department. Bill and Phil were friends. So Stratos knew all about my group and me, but I didn't know about him. He was several years younger. When I got to Greece, that's when I met him. And it was good. And also a guy by the name of George Christikos, who was Stratos' partner, who had also gone to Brown. So it's a small world. So that's the beginning of the story of the borates. It's a big story, but we studied borosilicates then, we studied alkaline earth borates, we studied using magnetic resonance, using neutron scattering. I had a sabbatical in 1996, studying borates using neutron scattering with Adrian Wright. So it's a whole big story of my career, the study of borates. But keep going. I think that's enough detail on that story.
Excellent, excellent. That's amazing. And you did all your research without hiring graduate students, right? That's amazing. You just worked with undergraduate students. How you managed to do all this research just with undergrad students?
Well, that's a good question. It is true that I do all my work with undergraduates. That's because of a long story too about what happened after graduate school. About the fourth year of my graduate school career, I began to think for the first time, what was I going to do after graduate school? Mm-hmm. Now you can go a long time without worrying about it. So I had gotten 4 years into graduate school. I never at all worried about a job afterwards. But at that point, I said, I better think about this. And well, most people of my group at that time had gone either into companies, Xerox at that time, IBM at that time, or they had gone to the Naval Research Lab in Washington, D.C. Amazing. Those are fine places, but I like to talk to people. I like to teach. I had worked with undergraduates at Brown, and by that time I was a senior member of the research group, so I had worked with new graduate students as well. So I decided to go and get more teaching experience. I had been a TA, most physics graduate students are, and then I became an RA, a research assistant. And that's where I was 4 years into graduate school. Well, I decided I wanted more teaching experience. I wanted to teach a class. At that time, TAs had helped with labs, or some had helped grade papers. I had taught labs, which was fine, but it was canned. By canned, I mean no originality. You just followed the directions. I could do those undergraduate labs. I helped the undergraduates, but it was not very exciting, to tell you the truth. So I decided I wanted my own classroom. So I went to the department chair. His name was Phil, too, Phil Stiles. And I said to him, I'd like to teach a class. And his response shook me a little bit. He said no. Why? Because he said basically a student who's going to Brown University, undergraduate, is not going to get a graduate student because they're paying in today's dollars $75,000 a year for school. For that, they don't get a graduate student. And I said, I respect that. But I had a copy of the college catalog, and I had turned it to the physics department, where it said that it trained teachers in the graduate school. I said to him, where's the training of the teachers? They had no courses, nothing at that time, no seminars, zip. So, and he said, that's a good point too. So we compromised. He let me teach a self-paced class. I was the teacher of a class in which students did the work on their own, and then they would come in for help, and I'd give them exams, and I would have small sessions, maybe 5 students at a time, when I went over the ideas. And that was good. Okay. Then that lasted 1 semester, and I became an RA again. But I decided at that time, the NSF grant that Phil had was paying my tuition. So I was getting tuition credit, basically thesis credit. So I thought to myself, I don't need that. Let me take a few classes in education. Let me learn more about teaching. Yeah. So I took a few classes in education. Most of them were useless. I had been told that they would all be bad, and that was a bad idea. Went back to Phil Stiles, the chair. He said, no way, again, because that would take money away from the physics department. I said, I want to do it. He eventually agreed. And there was one useful class I took, educational psychology, where we went into schools, high schools, and observed what teachers do. And that was an eye-opener to me, that the teachers do not talk to everybody in the class. They go to their favorites pretty fast. And that the people in the back of the classroom don't have to pay attention. Mm-hmm. And so that encouraged me to walk around the entire room when I was teaching, if you see what I mean. And don't go to the few who are willing to answer the questions right away. Yeah. And wait for people to answer questions. A lot of teachers won't wait. We actually made observations. We marked, timed. And that was an eye-opener. So that was a good class, actually. I learned a lot. Okay. Then I became an RA again. And now I'm I'm basically about a year from finishing, and I saw an ad in the Providence Journal. So I'm giving you details. This is, a lot of detail. But the ad in the Providence Journal was for Providence College, another college in Providence, Rhode Island, and they were advertising for adjunct faculty. They wanted cheap labor. But for me, it was an opportunity to teach classes. So I went to Phil Bray, who by that time had me fill in for him when he was on trips. I was the only graduate student to ever fill in for him. He was an excellent teacher. And so I had the big auditorium with a couple of hundred people, and I was learning skills about teaching. But then I could get my own class at Providence College, and he agreed. In fact, we agreed that I would spend an extra 6 months in graduate school, which for me was no problem. I wanted the experience.
Yeah.
So I taught several classes at Providence College. Then I graduated, and I knew that at that point that I didn't want to go to a big school necessarily. I wanted to go to a school where teaching came first. I applied to about 30 colleges. 6 gave me interviews, and I ended up at Coe College in Cedar Rapids, Iowa, where teaching does come first. But there are no graduate students. This is the short answer to your question. But I thought it was natural just to think, I'm going to do research. That's part of my job. I never thought one way or the other about it. And I had to think to myself, what can undergraduates do? We could build roller quenches. I could work with them for several years. The key, by the way, is to start them early. Start them the first day they enter college. That way they have 4 years. You would be amazed as to how much an undergraduate can do in 4 years. Do not wait until they're a senior. That's bad. That's a bad idea. Start them very early. Get teams working together.
Yeah.
Eventually, I got to hire other people, Mario Afatigato, Kyle Bragato, and others, and we built up a group. Having a group is very important too, of like-minded people. You don't have to have graduate students. The traditional model, it's not a bad model, but to me, the true teaching is at the undergraduate level. Well, for me, you can teach at the graduate level too. But generally speaking, what I saw is graduate students kind of do their own thing, and they meet with the advisors every so often, every week or two. But that world didn't impress me for what I wanted to do. I wanted to work daily with students. And, they can accomplish a lot.
Yeah.
And the glass field has been very good for that. So the work expanded. Every sabbatical allowed me to send students to the cooperating labs, even up to Canada, to Manitoba. I sent students at around 2000 in that case, 2000 to 2005. I've worked with many glass scientists around the world. As I mentioned, Adrian Wright and Stratos Kamitzos, Edgar Zanato in Brazil.
Mm-hmm.
I sent students throughout the United States, Iowa State University. And then slowly but surely, graduate advisors who became my friends in the field began to call me and Mario, for undergraduates who had promised to go into graduate school. So we began to send students all over the United States and some to Europe as graduate students, which we continue. And the group grew, and we were able to get NSF support from about 1986 until the present. We've never missed support, and the college has been supportive. And we've gotten grants from the state of Iowa and local foundations and companies, Corning, and others, to build this thing up. And we began to write equipment grants so that we have in-house now a very fine set of equipment for students to use. So that's the long answer to a good question.
Thank you. Yeah, that's amazing. We have in summer we have undergrad students. They would like to do research in the lab. They are enthusiastic about doing research, but they are young, and with no experience. And I can imagine how hard it is to work with them, to train them, to actually learn them. I mean, to teach them, and That's amazing. Yeah, and you've shown that this model also can work.
Well, it turns out that today was the first day of the summer research for this,
Okay.
for this summer. And we have a system. Today,
Mhm.
we met them. We went over the basics of keeping a notebook. We go in detail. We assume nothing. And also, we have a tradition at the beginning of the research. We clean every laboratory
Mhm.
from top to bottom. The students get to know, therefore, about the labs, and we start fresh. Every lab, every surface is washed and cleaned to begin the summer research.
What makes doing research in glass more challenging, in particular when we are working on borate glasses?
It's easy to get fooled. For example, when I mentioned the carbonate retention, which now know happens because of much experimentation,
Mhm.
at first, what we saw was that when we make glass, I have the students weigh the glass starting materials, say the lithium carbonate and the boric acid, and then we weigh it after we heat it to make sure that the weight matches the theory.
Yep.
Every sample. I don't assume that we have the right composition. And so that's a quality control step.
Yep.
And in the case of the sodium borates, we began to see that there was a discrepancy. The weight loss was under what we predicted. I thought that was because the sample was absorbing water at the high sodium contents. They're very hygroscopic. So I thought when we measured the weight, what we were seeing was water absorption. But it turned out to be carbonate retention. We actually measured the amount of carbon in the sample, and it matched the weight as difference quite well. But we got fooled at first. It's easy to get fooled. One can make assumptions which are not correct. So that's a challenge. You have to keep an open mind about what the results mean. That is to say, you can't have preconceived notions of what it should be. Sometimes you get results that seem odd. You have to keep an open mind there too about maybe it's real.
Mhm.
In one case, it turned out the student had switched the starting materials. We eventually found it that he had switched the starting material one time. Or I had a student, for whatever reason, didn't mix the sample, had
Mhm.
put the starting materials and then the next starting material into the crucible, and then mix them. I found that out eventually too.
So how how you learned it?
Because the weight loss wasn't correct.
Mhm.
And when I eventually got to the idea that he had switched it, then the weight loss agreed with the theory. I had some very rewarding moments. I told you that when we started from oxide starting materials, we got the more fundamental glass forming range for the binaries without the carbonate. Well, I was in Japan on a trip to visit my friend Masao Kodama, and we were talking about glass formation. He was very fastidious, very careful, um, and he told me the standard limits that have been published already. And I told him, no, those are not correct, because if you start from oxides, you don't get those. And so he tried it. I was in his lab when he tried it for the first time, and he was jumping up and down with joy when he saw that what I said was correct, that he had gotten these new glasses, and it was one of those moments of discovery, if you would. That's the flip side. That's the exciting moment. And students have made discoveries. For example, once a student came to me who was studying the lithium borate glass transition temperatures, and at about 5% lithium oxide content, he said that he couldn't find the glass transition. Now, that was odd, I thought. And so we began to investigate that. It turns out the width of the glass transition is a function of the composition. I didn't know it at the time. And we learned that lithium has the widest width of all the alkalis. In fact, say the cesium borate at 5% has a width of about 25 degrees, depending on how you define it, of course. But it's about 25 degrees wide. Whereas the lithium width is about 75 degrees wide. Same composition. And the reason he had not seen the glass transition is that it was spread over such a wide temperature range that it was hard to see it. But eventually we found it. We measured around 5%, at 3%, at 4%, at 5%, at 6%, at 7%. And that became a paper of ours eventually. That, lithium has an anomalous width. And what I did is I went back to my friend Marcel, who makes the best glasses, he passed away, but he made the very best glasses, the most precise and careful borate glasses that anybody makes. And he published the actual glass transition temperature thermograms. And he also showed the width. He had not worried about it.
Mm-hmm.
He didn't know that you had to worry about it. But in his data, we could see the same width changing right around 5%. So we knew it was correct. And one of those moments of discovery again. But that's also a challenge.
Yeah.
Again, a preconceived notion. We didn't expect the width to be changing, but it was changing.
What are the most common mistakes that you have seen in the literature when you are reading an article or you receive an article for review? When in particular again, borate glasses or generally glass science?
Oh, one mistake that I see frequently is that people will try to publish a paper with maybe 4 glasses in a system. So you're not getting the true patterns. Maybe they're in a rush. Maybe they don't know better. I don't know. So that's a very common mistake. Insufficient data.
So do you immediately reject it or? Okay.
But in a kind way, I try to be kind, pointing out that this is not complete. The work has to be continued. The next one is no error bars. So that's bad too. A graph without error bars or without discussion of the errors is incomplete also.
Yeah.
A lot of people don't check the literature. You have to check what other people have done to see if your results are reasonable. A lot of people don't do that either. So, there's a lot of messy work out there.
Yeah.
And you begin to learn who does the careful work, who doesn't do the careful work. But I feel for those who are trying to get into the field, and they might be, in some ways, I'm at a small college. I'm out of the mainstream. So I know what it's like to be out of the mainstream. When we made our first lithium borate study, up to the 73% lithium oxide, we spent the whole summer measuring the density. We developed the means of measuring the density, because when you get up to very high alkali content, you only have small fragments of the glass from rapid cooling. So we did a sink float method where you didn't need much glass. But I wasn't sure it was right or wrong. I knew that we agreed in the low alkali region, but I didn't know about the high alkali region. No one had ever measured it above about 35 mole percent lithium oxide. So the second summer, I had the students redo the entire set of measurements. By the time the second summer was done, I was pretty sure we were right, because we got essentially the same results again, independently. One of the biggest mistakes, and that's been extensively studied by my friend Stratos, but I've observed it as well, is that people don't use the right crucibles. We use platinum for most systems. For the alkalis, platinum is quite decent, except that high alkali content, you have to be careful. Some people use porcelain crucibles or alumina crucibles. Well, that alumina is going to enter the glass.
Exactly.
So you have to be aware of that.
Mm-hmm.
Yeah, so you have to worry about the purity of your samples.
Exactly.
And, chemical analyses of the samples is also important. At least until you know that what you're making is correct by the weight loss. To double check it against chemical analyses is important. We did that. That's how we found out about the carbonate retention. So those are some examples of the challenges. Keep going.
Yeah. And now people know that what they should think about. I mean, when they wanna submit the articles and they want to do their research. Yeah, these are the things that they should be aware of. I know that in gases, we got 3 and 4 coordinated boron. A couple of years ago, I read an article. I think it was not in the glass science, but they claimed that they have, I think it was a crystalline material. They claimed that there is 2 coordinated boron. Does it exist?
I think it does actually. So I know that through a guy in Austria, in Innsbruck, Austria, Hubert Huppertz. That's his name. He specializes in borate crystals, making very exotic borate crystals. That's a specialty. And yes, he has made some with two coordinated boron. But to my knowledge, in the glasses, they under normal conditions they don't exist. Normal conditions, standard atmospheric pressure and temperature, room temperature and so on. I don't believe they exist. But you can have two coordinated borons.
When you started your career, you mainly used NMR as the characterization technique for studying the gases that you made. Recently, I've seen that you also considered Raman for characterization. Is there any specific reason? Was there anything, any questions that you couldn't come up with the answers using NMR?
So this is a question of practical nature. When you have lots of collaborators, you are able to do different techniques, and each technique has its advantages and disadvantages. I went to a small school. It was impossible for me to have in-house solid-state NMR. Too expensive. So at Coe College, we don't have solid-state NMR. But through the kindness of people like Scott Craker or Diane Holland in England, Helmut Eckert, I've had access to NMR around the world. And we and with Steve Martin at Iowa State, we are able to do the fitting ourselves. I'm quite familiar with DM Fit, and we wrote our own programs, for example, to do boron 10 NMR analysis. And we wrote several papers on boron 10 NMR. But eventually we were able to get our own Raman spectrometer. Now, Raman is inherently qualitative. You can't get the N4s easily from Raman spectroscopy because of the differing cross sections. But you can get information about the intermediate range order. You can do that from NMR too a little bit. But Raman gives you some advantages. One, it's far less expensive than NMR. On the other hand, I also do neutron scattering, which is far more expensive than NMR. You need a national or international lab to do neutron scattering. And you have to have the expertise to do it. So on my sabbatical in '96, when I went to England with Adrian Wright, I was able to learn much about neutron scattering, and I continue to this day. Now I work with his student, Alex Hannon, and we do quite a bit of neutron scattering. So I use neutron scattering, IR and Raman. I learned about those with Stratos Komitsos, then we got our own. I do NMR to this day with groups around the world. So Scott and I have several papers using boron 11 NMR. We were able to use our rapid quenching to make TeO2 glass. We were the first to make it. Pure TeO2 glass. Then I visited Stratos Komitsos maybe a year or two after we published the result we had Diane Holland's group, we had Emma Barney come visit us, and she roller quenched TeO2 into glass. But then Stratos Komitsos had a graduate student named Naya Tierra who began to make bulk TeO2 glass using a cooling, not roller quenching, but a thin layer of the TeO2 melt in a crucible and dip that in ice water. And that made gram quantities of TeO2. I was there and I asked her, please show me this. Okay, so I saw the TeO2 glass being made. Well, when I got back to Coe, I got some students together, and it took us a couple of weeks, but we were able to do it also. So then I contacted. No, we presented a paper at a meeting, and Joe Swanziger saw it.
Mm-hmm.
Joe Swanziger's in Halifax,
Yeah.
Nova Scotia, and he asked us for some. He asked us for some TeO2 glass enriched in 017. So I said, send us the TeO2 and we'll try to make the glass. I'll never forget it. So we had several students who became good at it. The first one who became good at it was a guy by the name of Anthony. And Anthony now works at Corning. And I remember we got the powder enriched in 017 that Joe had made. And I was in the lab the entire time because it was expensive. So we went through the standard practice and we melted it and cooled it. We coated the bottom of a crucible. We dipped it into the ice water. And when it happened, it crystallized. We did it again. We remelted it. It crystallized. I was getting a little nervous. But the third time was the charm. It made 100% glass in the brand new platinum crucible. We got it out. We shipped it to Joe, and he was able to get the 017 signal. So we got several papers. We sent some to Sebiasachi Sen in UC Davis, and he did 2D NMR on it. And we did some tellurium NMR, tellurium 125 with Diane Holland,
Mm-hmm.
and also Joe did some. And before you knew it, we were characterizing TeO2 glass. And Stratos did the Raman and the infrared measurements, and we measured the density of it. We did an X-ray study of it to make sure it was glassy, the works. So
Amazing.
that's a long-winded answer to your question, too.
Yeah, thank you. So let's move to beyond the lab. I have also some questions about your the other aspects of your interest. I mean, you are a serious coin collector, and by serious I mean you have published articles, right, in this area. Would you tell us how you became interested, and tell us more about this interest?
Well, I know I was collecting coins by age 7 because by age 8 I was exhibiting coins. So, but those are U.S. coins, sort of standard coin collector thing. When I went to graduate school, I happened upon a coin show in Boston just by accidentally. I had, when I went to college and graduate school, I had not worried about collecting for a while. But then I found myself into this. I was visiting Boston, and this hotel advertised that they had a coin show, and there were maybe 200 or 300 dealers there. Well, one of the dealers had this money used in World War II in some of the camps. I had never seen such a thing. And I bought a set. And when I got back to Providence, when I was driving home, I saw a coin dealer. So I thought, I'll stop and see the rekindling of the interest. Well, he had a little booklet by a guy by the name of Ollie Slaybar, his name is, who had written about camp money of World War II. For $1, I bought the book. And in it, he had some examples of the money I had purchased at the show. Well, one thing led to another, and I began to collect it. Through auctions or coins shows, I became a collector again. Well, I have 2 daughters, and when they got a little bit older, I began to bring one in particular to shows with me. And we became a father and daughter team then. And she became a collector. And that's when she was 10. Well, now she's 42. And we're still discovering new kinds of money of World War II. We organize a conference every year on World War II money in Ohio. We write articles together about it. We give talks all over the world about it. In the National Japanese American Museum, in Little Tokyo, Los Angeles, and we've now given some talks on the money used in those camps. We just got another grant to study money of German American and Italian American camps. So American citizens in the United States were interned of Italian and German descent. Even Ellis Island, the famous Ellis Island where immigrants by the millions came, including some of my family. They came, and they were in World War II interned on the same island, in the same facility. So it's become a part of my life. I've written, I don't know, a couple of hundred articles now, and here I am.
Excellent, amazing, amazing. Also, you are an actor. In 2011, you played the role of Niels Bohr. Would you tell us more about this experience?
Well, I teach at a liberal arts college, and part of a liberal arts college is to teach first-year students what are called core courses or first-year seminars, something like that. And so I was team teaching with a theater professor. Basically, the course was science on stage, and I would explain the science behind various plays, and he would explain the theatrical side. Plays involving Einstein, Galileo, the famous Galileo by Brecht. We read that, and I would explain the work of Galileo, and he would explain the theatrical side. For example, I didn't know that there were 3 versions of that play that changed over time as politics changed. And so there was a play I had seen on the West End stage in London. I go to England quite often for research, but I love the theater there. So I went to the theater and I saw this play called Copenhagen around 2000. I think it was around 2001 or so. And the play Copenhagen involved Niels Bohr and Werner Heisenberg meeting in occupied Denmark and occupied by the Germans in World War II. It was a very strong play, extremely strong, about a dispute Bohr and Heisenberg based on true events. They disagreed on what happened at the meeting. And that was the end of the friendship of Bohr and Heisenberg, really, for the rest of their lives. Bohr had claimed that Heisenberg was trying to milk him of information about the Allied atomic bomb project, which Bohr eventually joined. Heisenberg claimed he was trying to tell Bohr that Heisenberg was in charge of atomic physics in Germany, had been the best student of Bohr ever. Mm-hmm. That Heisenberg was going to slow down the German atomic program so they wouldn't make bombs. Bohr didn't believe it. So they mistrusted each other. Now, the play was a brilliant adaptation of this. It went through the meeting 3 times to express the uncertainty principle of Heisenberg. 3 different outcomes of the meeting, depending on point of view. So we went over that play. I went over the ideas of modern physics in the 1920s and 30s, of what Bohr had done, what Heisenberg had done. Heisenberg got the Nobel Prize for the discovery of quantum mechanics, and Bohr for the atomic theory. And one day I did say to my colleague, let's do the play. We had done the class 3 years in a row, and Bohr had always been a personal hero of mine. And so we decided we would do the play and put it on at Coe College 4 times. We needed a Mrs. Bohr, so I asked my wife. And she turned out to be the strongest of the 3 characters. She was really good in the role of Margreta Bohr. And we did it. I learned the whole other world. It was a very powerful play, just 3 acts, hundreds and hundreds of lines. And we were sold out at Coe College 4 nights in a row, 4 days in a row. And we had about, I don't know, over 1,000 people come.
Wow, 1,000 people.
And then my colleague in England, Diane Holland, NMR spectroscopist, she's retired now, very fine NMR. She had worked with a guy by the name of Ray Dupree, who you might have heard of. He had done some of the early work of NMR in silicate glasses. Anyway, On her own, she applied to the University of Warwick in England Institute of Advanced Study to bring the play to Warwick. So the grant came. So Barbara, my wife, and I, not my Heisenberg, but myself and Barbara went to England to do the play. We got the University of Warwick students to become Heisenberg. 6 girls assumed the role of Heisenberg, about 700 lines or something like that. And Heisenberg, we folded the characters in and out seamlessly so that 6 different girls played the role of Heisenberg. We did one performance. The grant included a meal afterwards, an Indian meal. It was great. And it turns out, by coincidence, that the theater department is in the same building as the NMR lab. So I was able to do NMR for a month and do the play, rehearse, and it worked out. So we did it a total of 5 times. Of course, I had to go to the Bohr Institute after that. I was close enough to Denmark in England, so I went to the Bohr Institute, contacted the archivist, whose name is Felicity Fors, and she showed us around the Bohr Institute, where the scenes from the play had actually taken place. Well, then it occurred to me when I was there, and I saw some great sites that I knew from the play immediately. But it occurred to me, if she was the archivist, well, maybe she could show me some of Bohr's papers, the originals. So I asked to see them, and she said to me, Steve, if you had told me in advance, I could have got them out and so on, but it's hard to do that spur of the moment. So I said, okay, I understand. So we were walking through the institute. The Danish people gave Bohr an institute after we got the Nobel Prize. And she suddenly said, well, Steve, if you could see one thing, what would it be? Well, of course, I had done background reading on Niels Bohr, and I knew what I wanted to see immediately. In 1912, a year before he wrote the paper on the constitution of atoms, the paper with the Bohr model, the energy levels, and which agreed very well with experiment. In 1912, he had written to his boss, Rutherford, explaining his model of the atom for the first time on paper in a letter. I said, I want to see the letter. She said, okay. We go to the archives. She turns, the lights come on automatically. She climbs the ladder in the archives. She brings down the folder. She opens the folder, and she hands me the letter. The original letter. Being from Brooklyn, New York, I said, can I take a picture of this? My wife said, no way she's going to let you do that. She said, it was like this. Sure, go ahead. So it was a 5-page letter. I took pictures of it. In the margins, or in the back of the pages, there were little diagrams of the atoms for the first time, with the nucleus and the electrons going around, that Bohr himself had drawn. I had goosebumps. I was holding history in my hands.
Yeah.
The original paper on the structure of the atom. It was, and he had other atoms besides hydrogen. Today, we basically think of him as creating the model for the hydrogen atom. But he had done helium and lithium and a few other things. They weren't correct. So most people don't think about them. But in his original paper, he did attempt to explain them. And so there were the drawings of lithium and helium and hydrogen. They were just amazing.
Yeah.
So there you go, the story of the play.
Yeah.
I think that was a great experience, right?
Very rewarding. And my students helped me with the lines, and I was vulnerable during that time period. I spent about a month in the theater department at the beginning of a sabbatical, day and night in the theater department.
Amazing.
It was, by vulnerable, I mean the students got to see me, not so sure of myself.
What do you do at your spare time?
So I like to travel, I like to eat. In answer to your question about what do I like to do outside of in my spare time, I just took students to New York City
Hello.
and I showed them my New York. We went to my neighborhood where I grew up, but also we went to a Broadway play. We went to a New York Yankees game with my students. We walked around the city. We went to Chinatown. We went to Little Italy. We went to Wall Street. We went to Long Island. We saw the beach. And so I like to do that kind of thing as well. I go to baseball games from time to time. I like the game.
And you are a big fan of baseball, right?
I'm a fan of baseball. I have friends who are bigger fans than me, who know the game even better.
Amazing. So, what was your dream job when you were a kid?
To play for the New York Yankees. But and so I played little league like many of my friends, and we played um, baseball games on our own in on the concrete and in the backyard and in the parking lot. And by age 12 or 13, I knew I wasn't going to be in on the Yankees. I wasn't good enough, as most people aren't. So in my house, the education had a very high priority. I was a first generation college student. My parents hadn't gone to college, and in fact, my parents hadn't driven. I was the first to drive in the family as well. We took public transportation with the bus and the subway. Um, so that would have been a dream job, but as it turned out, impossible as well. Eventually, I told you the story of how I became a teacher, and that has worked out. I still like teaching. I'm going to start my 46th year in the fall.
If there were an imaginary world, another parallel world, what's your job over there?
Imaginary world.
Yeah.
Chef.
Chef. You do cooking?
I like to cook. My wife and I both cook. Tonight, later on, I'll probably make a bunch of meatballs for tomorrow's supper. I'll do that tonight. Every year I cook with my students from time to time. You know, to celebrate holidays, I cook. So to be a chef, that would be fun.
Yeah.
You know,
Yeah.
it'd be fun to be on like the Great British Bake Show. I'm not very good at it, but you asked me of a dream job. Being a chef would be fun.
Yeah. If a time machine existed, you would travel 100 years ago or later.
About 100 years ago, I'd love to have worked with Niels Bohr in Denmark, you know, to visit the Bohr Institute with the likes of not just Heisenberg but many great scientists when they were making the fundamental discoveries of the century. That would have been fun.
Yeah, yeah. I also would like to go back if it were possible. And do you have any regret in your life, in your personal, in your research life, academic life?
I've been pretty lucky, pretty fortunate in how the life has turned out. Do I have regrets? I should have exercised more. Probably eaten better foods, but I like to eat good food, so no regret there really. But exercising would have been smart. Although I'm pretty healthy still, I'm able to get around and everything. I'm 73 years old, in pretty good state of health. I don't regret. I mean, I think I could have made a lot more money, but I don't regret not making it. I'll tell you one quick story about that, maybe. When I was a sophomore in college in upstate New York, near the Canadian border, I worked for an Italian family who had a restaurant. They made very good pizza. At that time, my roommate was working making pizza, and he told me that the pizza place would deliver pizza by taxi cab. Somebody would call for a pizza, and they would send a taxi cab. I said to him, "Give me the fare instead. I'll deliver the pizza." Well, in 1971, Domino's came to town. The pizza, the cheap pizza place, and they advertised free delivery in 30 minutes or less, or the pizza's free too. And our business went down. So I thought to myself, a solution would be, and I went to the owner and I said to him, raise the prices of all pizzas $1 and say you have free delivery then. Because he used to charge $1 for delivery. I said, raise the price $1. Now we have free delivery. The business instantly quadrupled the next day. And I couldn't keep up with it. So when I was graduating from college, the boss, the owner of the store, came to me and said, Steve, when you go to Brown, open up a pizza place. We'll be partners. You run the pizza place in Rhode Island. I'll supply the capital. He had a very good product, 10 times better than Domino's. I had to think about it for a day or two, and I decided no, I couldn't do it. To own a pizza place, when I started the delivery business, I was working 80 hours a week. I finally hired physics majors to drive on different days to deliver the pizza. But for a while, I was working 80 hours a week for about 2 weeks. And, you can't do that for long. So, to open my own pizza place in Rhode Island, that would be 80 hours a week again. And I was at the beginning of my physics career. I'm not going to give up the career, right?
Yeah.
But at that moment, I knew I could have been a multimillionaire. Because he had such a good product and he was supplying the capital. We could have opened 1 store, then 2 stores, then 3 stores. It was all virgin territory. That was my chance to become rich. And I said no. I still think it's the right decision. I have told the story to students. And some of the students said they would have done it. But I'm convinced they made the right choice.
So, thank you, Professor. Thank you so much for your time. It was my pleasure talking to you and learn about your research and personal aspect of your life. Good to talk to you. Thank you so much.
And thank you for interviewing me. Nice to see you.
Have a good evening. Bye.